Victoria, if you could stop sharing. Our next speaker is John Mason, who's also been working with Dr. Hongwei Yang. John, I can see your slides. Please go ahead.
Thank you, Dr. Mystery. Today I'll be presenting on my rapid greener synthesis of copper BTC. So to start, I want to describe what metal organic frameworks are. Metal organic frameworks are cage-like structures that capture smaller molecules for various purposes. They're made by metal ions being attached together by various organic linkers. These can have applications for gas capture, such as addressing climate change, water purification to help in our difficult getting fresh water in different parts of the world, and then can be used for catalysis in various reactions. As seen on the right, we have a model of copper BTC where our green spheres show our smaller pore size. Our yellow sphere then shows the larger pore size. Eventually, we plan to use this for water purification of dyes and metals from water sources. In this research, an alternative synthesis method was used, observing the principles of green chemistry. This was achieved through microwave reactions, and where we were able to perform it significantly greener than the traditional solvothermal method. While we had to raise the temperature from 120 to between 150 and 185, depending on the trial, we were able to cut the time from 14 hours to just 10 minutes, which is 2% of the total original starting time. We then switched the solvent amounts from 200 milliliters to 15 milliliters, which is roughly only 8% of the total solvent used. This also allowed us to create the same amount of product, so we didn't have to scale anything back. For our synthesis conditions, 3 temperatures were observed, including 150, 170, and 185 degrees for 3 samples of copper acetate monohydrate. Then we observed 3 different reactants, all at 170 degrees. These reactants were copper nitrate trihydrate, copper acetate monohydrate, and copper acetate anhydrous. They were reacted in a 50-50 ethanol and water mixture in a microwave reactor at their specific temperature for around 10 minutes. After we created our samples, we had to then characterize to be able to tell what we made. For our first characterization steps, we used FTIR and X-ray diffraction in order to verify that the product was made in a similar, or we had a similar ending product as the traditional method. FTIR and XRD allowed for structural analysis and for us to observe the bonds. That we then used thermogravimetric analysis, or TGA, to find impurities such as water of hydration and byproducts such as acetic acid, and to observe the thermodynamic stability, which is incredibly important for copper BTC since it would be used in various different applications over wide varieties of temperatures. We then looked at the gas absorption for both surface area and pore sizes to ensure that our created MOFs were similar to the ones created in the traditional method. For our confirmation for using FTIR, we broke it into 2 different parts, one with reactants and one with temperatures. These were compared to the standard copper BTC bands. While looking at these, most of the peaks were the same between all of our samples, our copper acetate sample, our copper acetate monohydrate, and our copper nitrate trihydrate compared to our copper BTC. Our copper nitrate trihydrate had one specific band that was not present in the 2 other samples, but is also present in the bottom, or our standard. This is at 500 inverse centimeters. This band is due to a copper oxygen bond that is present in our copper BTC. Due to water of hydration that we believe was part of our structure, this bond can be disrupted and then not appear. Then observing the temperature, or then for observing our temperatures, we found similar results. The bands from, or the 3 different temperatures had very similar bands. Our copper acetate at 150 and 170 were both missing the peak at 500, where the band at 500 was present in the 185 degrees. Again, this is likely due to the disruption of water of hydration, which we were then able to deal with in our highest temperature. Our next way to confirm that we had copper BTC was through using X-ray diffraction. We compared this to literature values, where the literature values had peaks at 10, 12, 13, 19, and 26 2 theta. 2 theta is a description of the angles that the beam is both fired and received at in an XRD machine. These are very specific to the crystalline structure of copper BTC, and each crystal structure has its own various peaks at different 2 theta values. When comparing these, all of our samples had the peaks at 12, 13, 19, and 26. However, copper nitrate was the only one to have the characteristic band at 10. Again, this is likely to be disrupted due to the water of hydration that could be disrupting the copper bonding. Then we observed our thermodynamic stability. Our first drop can be seen, or this measures the weight % change over a time period and a temperature. Our temperature range was from 20 degrees to 430 degrees. Our first temperature drop was seen between 100 and 120 degrees, which is likely due to water and acetic acid evaporating. Our second, which is what we're looking for. Our second weight loss occurred around 300 degrees, which was likely from our decomposition of our copper BTC. This is compared to reference standards, and they also decomposed around 300 degrees. When we were able to observe our yields of our microwave synthesis, we found that all of our synthesis had relatively high yields. The reactants had very little change in between all 3 of them, even after the water of hydration was removed. The temperature yields were slightly different, with 170 being slightly less favorable than 150 or 185. However, since all of these yields were so close to one another, it's very difficult to make a determination just off of our yields. The next and possibly more important part of this compared to our yield is our surface area. This surface area is important because it's where we are able to hold our different gases that are captured and other molecules that get captured. The BET model is an estimation of our surface area by capturing nitrogen gas, and then the measurements are taken at liquid nitrogen temperatures and flooded with nitrogen. Copper BTC from copper nitrate and copper BTC at 185 degrees seem to have the largest surface areas, where the rest of them were around the same, or in the case of our copper acetate monohydrate sample, was significantly lower. For our pore size distribution, our second really important factor is our pore size distribution. These are to show that we have 2 very distinct pores, one being our green sphere and the other being our yellow sphere. These numbers are slightly off from what is expected, but that could be due to impurity in the sample. But our first peak is right around 150 angstroms, and our second peak is at 275. The first peak could be seen in the figure to the right as the 8 green spheres. This peak is peak is larger since there are more there are 8 spheres present per atom instead of just 1. After this was concluded, we concluded that our copper BTC from copper nitrate seemed to create our purest product with the highest BET and surface area, as well as comparable pore volumes. As far as our temperatures were concerned, we found that 185 degrees had the best surface area, while all 3 had comparable yields. Future work for this that another student will be completing is to use these MOFs for other forms of capture, such as dye capture and heavy metal capture, in order to test or in order to be used for water purification. The nice part about these metal organic frameworks is that they're reusable, so they can be cleaned and then used again instead of something that's traditionally used, such as a carbon filter, that can only be once and then is discarded. I would like to thank Dr. Yang, Dr. Yang for all of his support with this project and mentoring me through it, Dr. Baston and Dr. Sands for all of their emotional and logistical support, Dr. Saha for running our BET measurements, and then Dr. Jerry Poirier at the University of Delaware Advanced Characteristics Lab for all of his help. Thank you for listening, and does anybody have any questions?
Thank you, John. If there are questions in the audience, please unmute or add them to the chat. We have time for perhaps one question.
Dr. Baston is a question.
Oh, no, I was clapping.
Okay.
So I have a quick question, John.
Sure.
So this is amazing work and beautiful graphs. Did you have to do all of this at Delaware? Were you able to do a lot of it here?
So all of the synthesis, the microwave synthesis was completed here. Of course, IR was also completed here. This year, we just acquired a TGA, a working TGA device, which allowed us to complete that in the lab. The only things that actually were completed at Delaware were the XRD, or the X-ray diffraction. We were able to also, with the help from Dr. Saha in chemical engineering, he was able to run our porosity measurements for us.
Cool.